Hello.
Hey Ahmad, I can hear you.
Perfect. How are you doing?
I'm doing good. I know Boppy told me he might be a couple of minutes late, so
Okay.
but we'll give him a few and then we can start once we get a few more.
Sounds good. Thanks.
All right, let's give Boppy one more minute.
Let me bring up this presentation while we're waiting. So usually something fails in that stage. Wait. And can you see my screen?
We can, yes.
Okay, so the slide is there. All right, cool.
Okay, we have a lot, so the most important guys here. So I know Boppy mentioned he was going to be running late.
But
So
Bobby, yeah, exactly.
yeah. So Ahmad, do you want to get started?
Sure. Yeah. So, hey everyone. So basically, I want to continue the discussion we had for the app size, basically and basically add some bi-directionality or flexibility into it. So as we discussed, okay, this slide works. As we discussed last time, so there was a lower lane count, which already is in the standard, but we're proposing to sort of make it symmetric. Also, potentially, this way we can scale it down to 4 lanes. So that's an option we can add to it. Flexible TX and RX split options within a single file, which is what I'm going to show today. And support for lower clock speed, which is basically, it's going to be a slide, not much details that needs to be discussed on that. So last time we proposed the half lane, proposed the clock to be in the middle, and I'll go over it. The flexible TX and RX by signal scheme proposal, which enables lower pin count for lower speed applications. We have, if you have an asymmetric link, so your TX and RX sort of bandwidth are not the same, you can take advantage of it by assigning more pins to the TX versus RX or vice versa. We can potentially save a PLL on one side, and basically naturally within this protocol, we have a synchronous communication, meaning both sides will be synced to a single clock. So that has its benefits, and at least for IoT side might have drawbacks for a lot of other systems, but at least this is the way we're sort of proposing it. And then with lower clock speed, you can have lower and flexible data rates. So this is what we discussed. Basically, again, just rehashing in the past, this is the current proposal. We're proposing the clocks to be in the middle. So that's a typical single RxTX connectivity. This is how they look next to each other. This is how it's proposed they work when a half link is connected to a full link as opposed to what it was before. So we feel like this is a bit more cleaner. We last time discussed to have a sort of a table to have advantages and drawbacks. So I don't know how we want to go about it, but at least we have some advantages listed here. We didn't want to list drawbacks, but that would be something we have to work it out as a team. So I don't know what, I guess Elad or Bobby can decide how to fill these up based on the group inputs. So that's something we can have it dynamically as we go.
Yeah. So now sorry, I'm kind of reloading my cache a little bit. When you say symmetric half link, how should I say this? Like you're now, but this is just a bump map piece. This is not anything else. Is
just a bump map? Yeah.
Correct.
Yeah. This is just a bump map.
Thank you.
Yes. So now this is the sort of the new side with new part, which is, so we want to enable a single clock source across a TX RX line and across all TX RX line, and basically now start subdividing the pins between being TX and RX within a single PHY. That way we can enable a synchronous data link and maybe save some PLL at least on one side, one PLL at least on one side. And so at least this proposal is sort of meant for the 8 lane, but it can be expanded. Sorry?
Yeah, I'm sorry. I was just going to ask, so are you implying here that the receive side is to use its own clock recorded, or do you mean that you just want to loop around the received clock and use the root of the transmit clock in the other direction?
We basically routing around the clock that quote unquote you get from the receive side, but we won't call it the receive side anymore because it's not necessarily only going to be received.
Well, I think I understood, but maybe just clarify. So on the what you're calling the base chip here, in other words, the one that is not PLL. Physically, the way it is configured is that it has a clock forwarded into it, from the host chip, its received direction macro, and that the output of that PHY, at least conceptually, it could chiplets,
Elad, you're cutting in and out.
A little choppy.
Yeah, very choppy.
Oh.
Could you repeat the
Yeah,
question?
sorry about that.
No worries.
Yeah, am I any better now, by the way? Or?
Yes, you're better.
I think so.
Yes.
Or is it
Yeah,
let's
that's
see
better.
Yeah, sorry about
previous?
that. Yeah, so what I was trying to ask was on what I suppose you're referring to as the device chiplet. In its receive direction, it has a clock forwarded into it, and conceptually at the output of that receive phi, you're taking the clock that was recovered from that, feeding it back in as the root of the transmitter on the device chiplet. Is that correct?
Yes, but we don't really feed the clock. We just use that clock to send out the data.
Right, but conceptually, sort of that clock becomes the root
Conceptually,
of
yes.
the. Okay.
Yeah.
Got
Yeah.
it. Okay.
So
Got it. Understood. Yeah.
yeah.
So that, I mean, this is a thing that folks have done. The thing to watch out for here is from an interop perspective, this would have some, let's say, interesting implications on how the electrical specs have to be written. Because what happens here is now that all the impairments you picked up, from one side to the other, you basically sort of have to account for how they now influence, in the other direction.
Correct. Yeah, there is obviously signal amplitude, but also all the jitter starts to accumulate. So there is a limit on the speed when we go this route.
Yeah, no. And by the way, I mean, it's not that that is certainly true. My comment was more directed at that. Somebody would need to go through and sort of figure out how to sort of define the electrical specs in this mode, such that you can actually guarantee interop. Because it's sort of now it's kind of the combination. It's not just sort of like the one directional link. It's sort of the two directional link, and so just the way all those all that math was done just needs to be updated so that you can make a statement about, okay, yeah, somebody wants to support this mode. Here's the particular specs they must meet, sort of on each piece.
Yeah. It definitely gets a little more involved in the interoperability piece. Or we can, so that becomes more of a sort of a specmanship we have to do to decide if this would be an addendum and somebody meets this as well, and then what we added, or does this universally apply? And so
right,
on.
exactly.
But yeah.
No, not to say it can't be
yeah.
done. Just that's somebody has to do that work.
Absolutely, and I understand. Yeah, I understand this is like a lot of it does have a lot of elements into the standard. But I guess based on the use cases we see on the edge, in the edge side, we feel like this is something that can help a lot. So,
and Elad, you're going to do all that work anyway, right? So we're good, right?
Well, you can guess the implicit point of that of me mentioning this, but yes.
I knew exactly where your concern was, so I might as well hit it.
Yeah, no, I'm happy to help folks who are doing it.
I know.
Yeah.
We'll need your help for sure.
Yeah. So I mean, this is a basic thing, and there is a lot of work to be done, and we're hoping to all work together to sort of ratify this, because we feel there's a lot of need in the customer side.
Right.
So, all right.
It makes sense.
Now
just
back,
as a complete side point or whatever, or side question, if this is mostly focused on sort of the quote unquote lower speeds and sort of lowering costs and whatnot, the other way you can handle this is just have silly ring oscillators on each side, and you sort of make it async. I suppose if you're trying to make very low latency, then that's the primary reason you might not want to do that. But just from a specking perspective, that is that's another way you can go about it.
Yeah. So the one thing is the latency that matters, but sometimes a lot of times when you're the device that's sitting on this other side is say an ADC, right? So it does benefit from having to pump synchronous data to the other side without any interrupt. So there is a lot of intricacies that having a synchronous link as well would help. I mean, one of them is latency, but also like time stamping, stuff like that.
No, understood. There's there's always obviously subtleties and all these things on how synchronous they really are, but yes.
Yeah. And I think it's already getting complicated as is. Like synchronicity helps a little bit to reduce some of the pays off some of the complication, you know. But again, yeah, that's
Yeah, no,
that's why
makes
we
sense.
feel like
Understood. Like I said, side note, not yeah.
yeah. No, I understand. No, I mean that's yeah. And at some point, if maybe for higher speed, we have to do some sort of a synchronization, some sort of a PLL anyway, if we have for JR accumulation and long distances. So there's a lot of ifs and buts we have to add into the standard or limit the speed for those sort of build up of JR to not cause issues. So there is discussions to be had. All right, so now, so what we're trying, but basically just going back, so we're trying to do an 8-lane, but expand it to 4 and 16 lane bow if needed. So there's nothing limiting us to the 8-lane, but as a conceptual, we brought it up in the 8-lane side or half link. We are thinking of introducing 2 classify, a host and a device side. In terms of footprint, they would look pretty much the same. The OGS and FEC pieces might be swapped, but other than that, the data and the clock, which are the most important, especially the clock being in the middle, makes it flexible for both, for a quite to be sort of be operational or can be designed to be operational as a host or a device type of PHY. Now, what does each of these mean? So a host PHY, as we are defining it, is a primary clock signal provider. So it's the site that has the clock, that transmits the clock. So it has the root clock, as you mentioned. And the data bus for the host IP should be flexible to have either TX or RX on any of its pins. So any of its pins can be configurable, should be configurable to one or the other mode. So it has to provide that flexibility because it technically has to support any device sort of PHY. But it's basically.
I'm sorry. Maybe I
just,
didn't see. Did you show the? So in your bump map, are there actually 2 clocks then? 2 pairs of clocks, I should say. Excuse me.
So it would be basically this. So this would be a host IP, host PHY, for example, right? But it wouldn't be TX anymore. So there's a clock pair going out, and that's it. So and this would be it. But in this time around, these data lines would not be necessarily transmitted or received. They basically have option to be both set to a transmit pen or a receive pen.
So, but I think then, okay. So then maybe my description previously, was probably incorrect then, because I think if there isn't an additional pair of clock bumps, that whether programmably or consistently is always in the received direction, it's no longer a clock forwarded link, right? In other words, the pins that are receiving are conceptually using, like there's no additional forwarded clock coming back, right? Like there's just,
exactly. Yeah,
that's what I was saying. It's an
implicit clock, but it's not a real clock. It's an implicit. So the data coming back is quote unquote carrying that clock back, but there is no implicit clock coming back.
Okay, I see. So then this is definitely this is definitely very different spec wise.
Yeah. It does require sort of some sort of and then that's why synchronicity becomes asynchronous. It becomes you really need to have a clock data recovery if you do asynchronous or a real frequency recovery per se.
Yeah, no, understood. I mean, I guess the trick here is that, I mean, effectively it's not really clock forwarded anymore in the sense of, you sort of, there is one root clock for everybody, and, there's a path you can define, but the sort of conceptual, the conceptual delay in that loop is much larger than sort of it would be in a normal clock forwarded situation.
Exactly. Yes. There's a little bit more intricacy involved in it.
Okay, got it.
Yeah, and I should have placed this picture down there so that makes it easier. I apologize.
Wait, I
right.
have a question for you guys.
Sure. Hey, there's no. Hey, how are you there?
No, don't. Yeah. Anyway, it's more like, why can't we just sort of take the same specs and say half the rate if like you're just reflecting the clock?
Because this is just completely different, Boppy. Like
You can't do
it's
that.
not.
You can't just sort of say like I'm going twice the distance, so I just like every tolerance goes
No.
up. It's kind of dumb.
No. Yeah, I mean, I guess the answer is no. You know, if you want to know why, then it's actually an intelligent question. But but yeah, the answer is no.
I think it's a great question, Boppy. I mean, it's magic, right? Just pick the spec out there, and then we'd let the engineers figure it out. I like your idea.
No, it's more like everything takes twice as long. So I'm just wondering why we just can't take half the speed.
So
Well,
your
it may not be
proposal is
it may not be
basically
actually a factor of two, Boppy. That's the trick.
Or it may be more than a factor of 2.
I mean, you just it's something.
Oh, that's right. Okay,
moment.
the volatility doubles, so the actual delay. Okay, I get it now. It's the volatility that's doubling the actual. Right. Okay, that makes sense. All right.
Yeah, because we don't know what's happening within,
When
like
the
what's
volatility doubles, the
happening.
spread is much higher. The standard, it's basically. I got it. All right. Thanks.
Yeah. So, all right. So that's basically on the host device, but basically it's basically a device that has the clock and sends the clock. The device phi is the part that's a little more harder to define or has more definition attached to it. So it operates on the clock that it receives from the host phi. So this should be either hard-coded or selected to register in a scenario that involve non-IoT links. So our imagination is that device phi, a typical device phi would be an ADC DAC, ADC DAC combo, or something that's on it needs asymmetric data. It doesn't need, it has a very edge type of nature to it. It can be a sensor, what have you, image sensor, anything or in between. So in that cases, your chip is sort of a device phi. It's not going to be ever a host phi, or it most probably won't be a host phi. And that's when we say, well, either hard-coded or have a register to make it sort of be always a device phi. And if you want to connect two sort of, say, FPGAs or to something within this link, you have to sort of assign one of them to be device. We don't want to, do stuff like they do in the Ethernet side, which they pick a random host or sort of a device or whatever terminology they use. That just adds significantly more complexity to something that's not necessary for a chip that's going to always operate in one mode or the other.
Yeah,
So
there's no need for auto neg or anything like that, right? So we don't.
Yeah, like working through those things, trust me, it can take half of the battle of the project without adding as much in this scenario. So again, now the next step is that the device that the transmit and receive pins should be also hard-coded or register set it before the communication is started. That's another thing that sort of makes things a bit easier because again, if you're a device side, you somewhat know as a sort of designer of the sort of system that how many bits you want to receive, how many bits you want to transmit. So most of the time would be hard-coded. So hypothetically, let's say you have a 12-bit ADC, and you want to just use you want to do a factor of 2 sort of serialization. So you assign 6-bit of it to be transmit, and then 2 bits for receive for whatever control or dynamic adjustment or whatever you would need. So that can be pretty much hard-coded programmed, or if your ADC has a flexibility, you change the register, or you change the EQs or something like that to justify in that manner. Moral of the story, the device side will be relatively hard-coded when the link starts, when this link starts coming up. And just as we basically want to standardize the bit order, so I just propose we start from the leftmost pin when the chip edge is facing the bottom and count upwards for the bit order. So nothing important, but just adding to the specs. So now this, what sort of entails is that what we have to sort of work through is the initialization and training routine. This initialization and training is a little bit more involved, but it doesn't, like we can skip certain steps if we do some hard coding on the host phi as well, which we can. But assuming there is no hard coding in terms of transmit and receive pins, the way we start is that the host I5 starts transmitting the clock to the device side, and device side receives it. We can have a timeout type of functionality for it to make sure it's receiving the real clock before it starts doing anything else, before going to the next step. After sort of that clock is established, the device side starts transmitting on its TX pins, and the host side will be receive on all of its pins. So pretty much waiting sort of on the hearing back type of mode. And whichever pin it starts receiving signal, it will count that pin as a TX, as an RX on the host side. Anything that it doesn't receive a signal, it assumes it has to transmit on it. So that's basically number 3. So basically that way it can sort of figure out, we can sort of negotiate which pins are transmit, which pins are received. So now if the device side has any TX pins, it will need to send signals to TX to help the RX phase optimization. I guess one thing I forgot here to mention, the clock going from host to device would have like a 90-degree phase offset in a sense, and this is dual edge signaling. So with the 90-degree phase offset, the assumption is like you can use the clock at least at the face value. If everything is sort of synchronous in the input of your device side, you can use the clock you're receiving to recover the data. On the host side, you have to go through a training. So this is where it comes to where the device side will start sending training data to the TX to help with the RX phase optimization. Because the TX has the clock locally, but it's not receiving it from the link, so it has to do an optimization there in the beginning. And basically
Sorry,
use
just
it
one
to adjust
quick thing.
Sure.
I guess, are you assuming there's no sideband, or rather, maybe I should say this way: is the intent to not sort of actually have a separate sideband thing? Like you really do want everything to happen over this?
Right now, that's how we're doing it. There's some of the useful information can be transmitted through sideband. Some of it can be actually hard coded, but this does not assume as much sideband sort of signaling.
Yeah, and I mean, basically, that's sort of what I was asking of, if you assume that there is a sideband, I think a lot of this complexity can be reduced or eliminated, right? Because I guess a lot of
we have the whole reason to do this is the cost factor, right? Unfortunately, because there are people who really no. I mean, I'm just saying. So that's one of the reasons to try and even get rid of the PLL and then try and just make it as low cost as possible. Right, because then it's actually lower cost than what they're currently using for ADCs and DACs and sensors. So that's one of the key value props, if you will. But you're right, it is taking some of the features that you could do through a sideband for sure.
Okay. No. Intent to the question was not so much to say that's what you should be doing. It was more just to double check that it was an intentional design choice.
It is, well, it's our design choice. We're obviously the group has to agree or comment back or
makes
say
sense.
They don't like it.
Makes sense. Yeah, I mean, it definitely
becomes.
Oh, yeah, sorry. Go ahead.
Okay. Yeah, and it becomes a philosophical approach. I mean, when I think about it, honestly, I wrote this, but I think about it, I think some of it is completely unnecessary because a lot of these things is basically sort of the way we did things in the links. We didn't really have control over both sides. In reality, when you're doing a chiplet, you're not going to change them. You can technically sort of register select them in the beginning. So there's a philosophical argument that do we need, even like quote unquote, some of these pin orders can be register selected before even the link comes off. So some of it is unnecessary, which I actually touched. So there's an argument to be had. Yeah.
Yeah. No. So maybe just the sort of the philosophy you're describing, is essentially the philosophy that was taken in the link layer, sort of so far, and the sort of, I think I'm largely going to be just rephrasing or expanding on what you said, but yeah, the philosophy that was taken there was that anything that is essentially not transparent to the user, we just, as you said, we assume that there is some magic entity that actually does know what the heck you're trying to do with this chiplet, because in practice, as you said, that almost always has to exist anyways. And that magic entity can go and just, program all those things that, would have never been transparent to the user anyways. And then the things that, sort of the phi plus link layer should be responsible for, actually sort of autonomously breaking up are things that really are transparent, right? So like training of, sort of phase offset settings or reference voltages or whatever it may be, or, redundancy, things of that nature, that makes sense for sort of the whole die-to-die subsystem view on its own. If the things that, just the user would have had to know about it anyways, then, just make use of that.
Yeah. Yeah. No, I fully agree. So I wrote in a whole thing, but as I have it here, there is an option to pre-program and just avoid steps 2 and 3. And I like this option, but I just had this listed so that for sake of completeness, but depending on the philosophy of the link, we probably can forego 2 and 3 steps. So that way, it also makes things simpler in a sense, because.
Wait, I've got a question. So won't the sideband have the same thing, that it has to get its clock from the transmit sideband?
No, sideband basically is defined with 2 forwarded, right? There's a transmit direction, there's a receive direction, and there's 2 forwarded clocks in each one. A clock has to come from somewhere, but it's assumed that if you're on a sideband, then either you've just created your own clock, or or you're deriving it from some other reference, or whatever.
But the intent of this is to sort of not, like, they'd have to do something, right? Otherwise, if you have to have a clock on the sideband, then what's the point? You might as well have a clock for them.
Yeah. Yes. In this one, we probably, as Kash mentioned, we don't want to involve the sideband
right.
as much because of the costs of the edge device, but there are things that we can have pre-programmed. Those are cheap. So those ones we can easily do. The sideband, in this scenario, we prefer not to use it just because of the size and the cost. I know in like larger link for sure, like there's a lot of benefit to not populate a lot of junk on the link itself, because you have a 32-bit link. Just having a few sidebands that does a lot of work for you saves a lot of the complexity on the 32-bit. In this case, because the link size is shrinking, some of those operations we prefer to do on the link itself, but a lot of it can be pre-programmed. The pre-programmed parts can be pre-programmed. So that's how I see it on this one. I don't know if that makes sense.
Yeah, no. So that makes sense. It is more the side. Let's think about a sideband. I'm kind of like, you would have to, if you sort of had an independent sideband clock, wouldn't you negate the advantage of, like you're saying, I don't need to generate a clock on this. It's a simpler device.
Well, you could argue the sideband clock and data doesn't need to be as high quality and high speed. So there is argument to be had on this, but the way we are encountering it in sort of working with people is that obviously every pin is valuable. So unless you can have a dual nature to each pin in the use case of this phi, it might not be a wise idea to use sideband again for this specific approach. For wider data rate, for wider phis, sideband is basically it's a very viable option, and adding those clocks is fine. But yeah, I think everybody is right. The way I'm getting at it is everybody's right.
No, man, it's only good if we're right and Elad's wrong. That's the only acceptable outcome. But anyway,
no.
He's hard to find, make him wrong though, right? Which is
yeah, that's the whole point here.
That's becoming very,
a lot of energy
becoming very problematic.
It's okay. You can just define me as being wrong, and then we're all happy.
That someone doesn't give us the deep satisfaction. But
it's hardwired. It's hardwired option. Elad is wrong.
Exactly.
So then I've got a second question. Like, what is the maximum speed at which we want this option?
That's a very good question. So we have to do some study on it to see how much. It's a little, that's one of the harder parts, because yeah.
What's the intuitive answer? Elad too. I mean, like, what is it that you guys see as the intuitive answer for, like, oh, this is going to be at, like, 2 gigabits per line, or 4
Yeah,
gig?
I mean 1 to 2 gig, where exactly, who knows,
Yeah.
but somewhere in that ballpark.
Somewhere in that ballpark is where you
Yeah.
can deflect the clock, basically.
1 to 2 gigabits per
Yeah.
second. Sorry.
Wait, 1 2 gig clock rate or 1 2 gig? I mean, it's still going to be DDR in
Yeah,
this, right?
gigabits per second. Now, I mean, I do think there's a valid question of whether you actually want to be DDR or SDR.
Yeah.
Because, yeah.
I think we want to be DDR. I think there's benefit of being DDR because it keeps all the sort of the quote unquote frequencies, max frequency on all the lanes the same. I think it would be 1 to 2 gig, but we have to do some analysis to see if we can, depending on the distance, we can meet a 4 gig. So it also becomes a trade-off between the channel distance, right? And it's not as much the loss as it is the latency, but the quality of clock going there and how much that quality degrades, and then when it goes through the system comes back, and then the data recovery. So there's a bit of involvement there, but we want to define a minimum for it.
Yeah, Bapi, I think the goal, at least internally here, is to try and have a 2 gig clock, so you do 4 gig DDR, right? So that's the hope, right? And then and it also depends on the process, right? So it's more complicated because, we've seen customers wanting like 90 nanometer. How do I do 90 nanometer or 65? Well, okay, maybe even if we get 1 gig, that might be good, right? So I don't know. But we chose not to put a higher limit, but that's just FYI, right? I think we talk about clocks on the next slide or something, right? Yeah. So if somebody can make it work at 8 gig, more power to them, right? But it's unlikely.
Yeah, there's definitely a limitation as we go up. Again, there's a lot of things coming to the picture. I think everybody knows. I mean, process speed is one of it. A lot of times, like sitting on the side is a very older process, but also like the length of the channel, like because all those uncertainties start to add up, and then and this mismatch between the lines. So it really comes down to a lot of specmanship. If those chips are like tightly next to each other, you can argue it can go very fast, because effectively it sounds like it would be basically a real in-chip communication at some point, right? So there is a lot of things we have to sort out as we go, which affects the high speed for sure. So I will get through this, but basically in the initialization, our host side will use the RX data to transmit to the device to adjust the host RX slicer clock to middle of the cycle, which means some sort of phase interpolator will be involved. I guess I have it here that the host side will align the 90 degree of the clock it's sending to minimize any need for clock adjustments in the device side. So that has to be there. We're assuming the device side will take care of any mismatch it introduces itself. So that's sort of a reasonable assumption. So as long as the host side transmitting sort of with the 90 degree in the middle of cycle, the device should be able to take care of it. And also compensate for its own sort of latency introductions. And all of this has to be spec'd out, I guess. When these are sort of set, we can start the communication.
Hey, man, sorry, can I pause here for a second?
Sure.
Yeah, so, and I'm sorry, you might have mentioned this previously, and I just didn't catch it. What was the primary benefit that you were seeking from sort of doing the 90 degrees?
The primary benefit was, I guess, more or less, I guess we can argue two things. One of it is basically that the receive side doesn't need to do, technically it doesn't need to do, or theoretically doesn't need to do any phase alignment for receiving the data. So hypothetically, it can use that same clock. Again, there is a lot of delays involved inside it. But hypothetically, it can use the same clock to receive the data or sample the data without doing anything on top of it. Does that make sense?
Yeah.
Elad, I think your audio may have.
Yeah. I hope it's back now.
It's back. So.
It's back now.
Okay.
Yeah.
Great. Yeah. So I think understood. I think for lower and where this boundary is, obviously depends, right? I think for lower data rates, where you can just sort of you kind of don't care about a lot of other things that have to exist in the path anyways. I think everything saying is reasonable, and you can kind of do it without any sort of like training involved. But at higher data rates, you sort of inevitably, 90 degrees isn't really 90 degrees. It's something that happens to cause the receiver to get lined up. And then that forces you to sort of do a training kind of, in each direction. Like, you have to have the receiver tell the transmitter to do certain things since the receiver's not, doing the movement anymore. And it just turns out from a very detailed architecture standpoint, one can show that, sort of basically the split point of the clock and the data is sort of like the sort of the thing that you care about, and this pushes that split point earlier than otherwise. So I guess where I was going with all this is that if you are interested in sort of supporting some of the potentially somewhat higher data rates, again, where that line is, I don't know either, right? But if you are interested in supporting some of those higher data rates, unless you were seeing that there was sort of a very obvious benefit on this, it may not, this wouldn't be one that I would sort of, immediately jump on saying, yeah, that's the way you'd want to do it.
Got it. That makes sense. Yeah, like the way I was thinking of it initially, and we might be doing this in line with the rest of the standard. If basically the way I was thinking is that the clock speed is lower, it helps you sort of not to on the device side. You don't even have to think about what the half cycle means. Meaning you don't have to do whatever latency you introduce. So you have the receive latency, right? You receive the clock and then you have to distribute it across your channels. Those are somewhat process dependent within the device side, and you have somewhat of a control over it. So as long as you can compensate for that, you can do something. But again, it's a very simplistic view. So the moment things start to sort of space start to go up, that starts to be a problem. So
yeah, no, I mean, I think you've got. Yeah, I think you've got all the right trade-offs, right? It's as with several of these things, it's one of those where as long as you're slow enough, then then there's a very good reason to sort of, or there are good reasons that that one would want to go this way, and then there's sort of just a quantization that happens of beyond some point. It's like, well, actually that's very painful, so it pushes you in the other direction, and so it really is a usage usage question, and one can I mean basically there's a few of these things that may end up being stacked up, and they may all push you towards the lower data rate, which is totally fine, right? Like if that's that's the target, then great. That's all felt consistent. It's really just more of a question of target than sort of than anything else.
Yeah, and one implicit addition thing that this 90-degree offset brings, which is again lower speed with all those sort of hypotheticals, is that it keeps the clock thinner while the data being transmitted. So in a sense, because we're using the same clock for transmitting on the other side, it reduces any potential, it sort of reduces a bit the data dependent jitter stuff on the clock. So that's an implicit, which is immaterial for a normal forwarded link. For this case, this brings that as a small side benefit, if it makes sense.
Yeah, no, but for low data rates, I think there's a valid argument there because there's enough time between sort of the middle of a bit and sort of the edge or whatever that some of the reflections and other things die off, and that does make sense. Yeah,
so that was the assumption in this, but again, it's some flexible assumption, and we have to do many more analysis. If the premises are okay with everyone, we'll do analysis and try to see where the dividing line is. But
sounds good.
All right, and so with all appropriate things adjusted, you can start the communication. On the host RX side, we might need to do periodic phase adjustments while the link is running to make sure the compensates phase drifts due to temperature and voltage movement. So that's a very general statement for something that needs to be very well defined, needs to be defined, meaning what type of phase drifts we can support and so on. So that again is something to think about. So yeah, because on the other side is the 90-degree guaranteeing, at least on the transmit side, is somewhat something we can do simply or easier. On the RX side, when we receive the clock, even if we have calibrated in the beginning, things will change with time, right? And that's something that the host, because the assumption, again, if you notice, the assumption here is that the host PHY is the more complicated PHY, the device PHY is a simpler PHY, and therefore we can do more on the host PHY and sort of offload a lot of things from the device PHY. So in this case, the host PHY will try to do some periodic edge phase adjustment to make sure it's targeting the right phase for the sampling. Now, I haven't mentioned, but implicitly the assumption is it would be the same clock for all the channels it's receiving on the host side. So that way it basically can take a sample, like it can do a round robin and just take a sample and see how to optimize the sample point for it. Or I don't think it's necessarily, especially for lower speed, to do per RX phase adjustment. So yeah, so with that, I think I'm done. And then, as I mentioned, we can get rid of the step 2 and 3 because we can potentially, and I think that's we might just not have it as an option, but have it as a sort of plan of record that things would be specified as a register. Because again, when you're putting these things together, you know what you want to do more or less, or we can program what you want to do. So the next thing is we're going to support as sort of a target 1G or 500 megahertz limit. We don't specify an upper limit because it starts to be sort of a challenge to. We have to do a lot of analysis for the link distance to figure out what's the upper limit. But for the lower limit, we want to sort of at least give it a low limit to people, so at least the low end is supported. I think that we have it as a startup at the lower, as a fixed clock rate, but again, we can potentially have those registers selected to what speed it starts up at. So I think maybe that's another thing that we can have these register bits specify the operation speed before the link is up, because again, the user has both sides clarified, or has both sides sort of has control on both sides and before even the chip starts. There is some fixes I need to go into the side, but yeah. Any more comments, feedbacks? I think that's the end.
I think that makes sense.
So wait, does this mean if you do this, you don't need those elastic buffers on either side?
Unless your circuit needs it, no, you don't need elastic buffers. Yeah. So at least, so give you an example, right? Again, the use case for this. Let's say you have an ADC and DAC sitting on. You have, say, a FPGA trying to read data from an ADC and pass a certain data to a DAC, and this is like some system, right, that has synchronous. So pretty much this link lets you read the data from ADC and pass it through the DAC without any adaptation FIFO, assuming those sample rates are all synchronous.
Thanks.
Yeah, so it simplifies latency, it simplifies. Yeah, so it has a use case which I don't want to call it niche, because a lot of the things in the field operate in these synchronous speeds. It's not just It's just that the higher end systems are not necessarily synchronous because of all the complexities involved, and everybody wants to have control over their speed for many reasons, FCC, so on. But in the edge side of things, there is a lot of benefit to synchronicity, avoiding, yes. So this enables that.
Yeah.
So the other way to think about it, this would be, I don't want to call it a dumb file, but it would be a dumb file. Basically just sitting there and just letting data pass through one way or the other.
Don't give Bapi ideas. He's going to call it dumb 5 2.0 or something.
Well, I'm an engineer, so my namings are gonna That's why you shouldn't put me in charge of naming or marketing anything.
Okay, I think that Bapi, I think that's it from our side. So
Okay.
would appreciate. I think.
So where do we go from here? What exactly happens?
Well, we need Alad to first do his holy water to it, and then obviously feedback from all the other members. And then let's
my holy water defined as being wrong has been granted.
Touche.
Wait. Okay, never mind. This is recorded. I have so many questions. All right.
So what I can do is I'll do some adjustments here. I'll sit with Kash, do some adjustments, and find a way to share it with the team. So that way, I guess Elad can do his magic. I said, oh, Elad, and I said you have a valid point. So
it's fun. I'm just having fun.
No, I know.
This is a question, not a recommendation for you guys. I'm asking, do we want to gather more people in the big group, or we should just settle this whole thing within our the group of people who show up? I'm asking, not recommending.
I would think it's good to have a big group feedback, but before that, we should get it to a stage where it's ready for bigger groups. And I think like some small group feedback would help to sort of get into a stage that when we present it to a bigger group, there's less holes in it, or has more eyes have stared at it. Because gathering feedback from a larger group, it starts to be challenging. So we want to get it to a certain stage that at least those obvious things we know is not obvious issues, or I guess disagreements is not present anymore. So
okay. Before
we present a larger group. I don't know if that makes sense.
That makes, so then the only guy I can think of who probably we should sort of deliberately yank on this is Marek. He sort of showed up last week, but then he isn't here this week, but he's the only guy we should sort of actively nudge and say, give us your thoughts on this.
Sure. So
yeah,
what I can do is like clean this.
We'll send him.
Wait, and Tom,
we'll add him to the group. Obviously, I've been sending it to you and Elad, right? So yeah. We'll add him to this and get his feedback. Andrew's with a ADC company, right? Andrew, do you have any feedback, or do you want
to? No, I don't have any feedback. I agree. Marek probably have a better insight than I do.
Okay.
Oh, wait, if you got 10 minutes, gosh, you're in so much trouble. You better pull up that line from the business paper that I want Elad to hear it.
All right. Should I stop sharing for now?
You're trying to get both of us in trouble, huh, Bapi?
Yeah.
No, just gosh. He is slandering us. Hang on. I will get that.
It wasn't meant to be a slander. It was meant to be what was the right word? I don't even know.
Yeah, keep searching. Meanwhile,
I don't even know. I have to backpedal quickly.
Okay, when I read them to you, Elad, your blood too will boil with righteous indignation.
So it was meant to be an impartial observation.
Well, while you're searching for that, blood boiling quote. Copy. This is Kevin. So,
Yes, Kevin.
like Elad, a lot of the asymmetric ideas here make sense for certain applications. They're used in memory a lot, but it's very different than Bo. So I'm not sure how does this fit into the specification world? Is it a different spec? Is it somehow an addendum to the Bo spec? It kind of uses a bump out, but it's really not a Bo-Fi at all. To me, it doesn't seem like, other than having configurable bidirectional, lanes. So I'm just not. I'm confused about how this gets handled logistically from a spec standpoint.
One of you guys want to do that? Or you want me to answer? I'm asking. Elad? Or
yeah, no, I mean, I think it would have to be a sort of separate mode, so to speak, or arguably a different phi, as you were saying, Kevin. Because I think that there are going to be a lot of differences there. I think the primary, let's say, reuse factor is probably mostly just from the spec setup of which electrical parameters you need to worry about and which sort of timing parameters you need to worry about and things like that. There probably are a couple of unique ones sort of here, but yeah, I think it would just be a different mode is my guess.
Okay, thanks.
all right, I found slanderous quote, but unfortunately we're out of time. But anyway,
I'm saved.
Yeah.
You can say the quote and Elad can comment on it.
Let's keep it a happy meeting.
Yeah, happy meeting. Okay, let's go with a happy meeting.
fine. I will email Elad the reference, and we can respond offline.
Okay,
sure.
Yeah,
that's fair.
You guys can meet in a parking lot and sort of get.
Problem is, I don't know where Kash lives. I got to hunt him down at conferences. That's a challenge.
I live in a Starbucks coffee shop or a Pete's coffee shop more than at my house these days. So it's crazy. All right, guys. Thank you.
All right.
All right.
All right. Thanks a lot. I appreciate it.
Thanks, everyone. Bye-bye.
All right.